We wish to now begin talking about the force due to a magnetic field. And we need to point out that there are some things that make this force very peculiar compared to what you have seen before. Now, the way the magnetic force is defined, and often we'll use this subscriptive B for talking about the magnetic field, in part because we've used the letter M for other things, but in general we tend to use the capital letter B for referring to a magnetic field. Sometimes we'll call it the B field. And just to point that notation out, the force, though, from a magnetic field is dependent on a few things. One, it's going to depend on the charge of an object moving through. So much like an electric field, it is a charged particle that is going to ultimately be affected by it and have its motions changed. So how big the charge is, that much makes sense. We would also expect it to have some sort of relationship to the magnitude of the B field, of the magnetic field. Again, somewhat similar to what you expected from an electric force. But there's another feature that makes this rather peculiar. One is that the charge in question needs to be moving, so its velocity comes into play. So this is already a little bit different. I could have a static charge put in an electric field and it would be accelerated. On the other hand, with the magnetic force, if a charge is not moving, then it will not be affected by a magnetic field. But more than that, also notice in this equation, I have two vectors. Now, if I were to multiply the two vectors together like the dot product, such as when I'm finding, say, work, then that's going to give me a scalar. But force is also a vector. So if you remember that there's only one way of actually multiplying these two vectors together and getting a vector outcome is if we have to do the cross product of these two vectors. So you've seen something like this before when we talked about torque last semester, where in that case the torque vector was based on the applied force in cross product with the lever arm vector. So the dot product, which if you did that, you would have the magnitude of the two forces multiplied by cosine theta, where theta is the angle between the two. With the cross product, if you have A cross B vectors, that is the multiplication of vector A, vector B, their magnitudes, multiplied by sine theta, where theta is the angle between the two vectors, and which would indicate to you that you would get a maximum value when the angle is at 90 degrees. So the same thing here then with the magnetic field, that the magnetic field is strongest when your velocity vector is perpendicular to the magnetic field vector. Now, because this is going to become a bit confusing, it's necessary to also now bring in the idea of the right-hand rule to put together all this vector notation and multiplication together. So here's a lovely picture of my hand. You don't have to talk about it now, I know it's nice, but we can move beyond that. And I have extended out my index finger, my middle finger, and my thumb. So the way we use the right-hand rule is that if we have the index finger pointing in the direction of the first vector that we're multiplying, the middle finger pointing in the direction of the second vector, the thumb then points in the direction of the resultant vector. So now remember that I had said that the magnetic field force is defined as QV cross B. So velocity is the first vector, so that would correspond with my index finger pointing out. The B vector is then corresponding to my middle finger, and so that means my thumb is pointing in the direction of the force, and then also that means in the direction of the acceleration of any sort of charged particle moving in a magnetic field. So the reason we have to use our fingers like this is because each one of those vectors is perpendicular to the other. So V and B are perpendicular to each other, but F is also perpendicular to V and perpendicular to B. So everything's pointing off in its own direction. So if V is pointing in the X direction, B in the Y, F is in the Z direction. So that's something also that's going to be very strange compared to the magnetic field force. You get force not in the direction you're going, not in the direction of the field, but perpendicular to both, in a completely different plane than you were traveling in. Now let's imagine what this would actually mean for the motion of a particle. So I have drawn here a bunch of blue X's to represent the magnetic field. And because it is this X or cross shape, this is to say that the magnetic field is into the screen or into the paper. Why this sort of symbolism? If you'd imagine it was an arrow, then you're looking at the back end of the arrow. So the arrow is going into the board or away from you. So you're seeing the back end of the feathers of the arrow. If it's a dot, that means it's coming towards you or it's coming out of the page or the screen. So let's imagine we have this sort of constant magnetic field, and we want to go ahead and insert a charged particle of some sort in that field. So if we just set a charge there, it doesn't move, so it's not going to actually be affected by the magnetic field at all. But let's give it a velocity vector, and let's have it just point straight forward. So that'll be our velocity vector. All right, well, according to the right-hand rule, if the velocity vector is forward in the direction of my index finger, and my middle finger needs to point into the screen, so this actually is going to cause my thumb to point to the left here as the direction of the force for the magnetic field. So in this case, you'd actually expect it to start curving the path. In fact, really in particular, if you look at it, you realize this looks very similar to what you'd expect from the centripetal force. And indeed, what will happen is the object is going to go around in a circle, and the magnetic field force is always going to point towards the center. So a charged particle can't move in a straight line in this sort of constant magnetic field. It's going to go around in a circle. Now, this is assuming that the magnetic field and the velocity vector are perfectly perpendicular to each other. If it's not, then you could actually have it not just spin around in a circle, but the center of that circle moving forward, and you could get some sort of helical shape of it moving around. But at least in this simple case, you can see that we're pretty much reproducing circular motion just by taking a charged particle and moving it through a magnetic field. So notice again, all these vectors are perpendicular to each other. It is not necessarily what you'd expect on your first thought of how forces ought to work, but this is the nature of the magnetic force. But let's complete how weird the magnetic force is actually, because you are used to seeing magnetic force in a somewhat common setup. If I pull out a bar magnet, you can tell me that there is a north end, a south end, and if I bring something metallic such as an iron nail towards it, then you know it's going to get attracted. So if I put some sort of a nail here, you would expect it to be pulled towards that magnet. No problem. However, this should be a bit weird because, again, the force that describes magnetic force is supposed to depend on the charge and the velocity of your charged particle. The thing is, though, if I have an iron nail just sitting out, it's not necessarily charged. And if I just have it laying there, it's not moving compared to the magnet here. So why in the world would it even get pulled in the first place? The problem is that to fully explain the magnet as we know it, we actually need a quantum interpretation of what's going on with the particles that are zipping around inside the magnet as well as the iron nail that we have. So it's going to be quite a few steps to go from the basic points of magnetic field force to ultimately the magnetic that you have on your refrigerator, that you've seen as a child, even the electromagnets you might have built at a younger age as well. This is just to get across the point that there is a strangeness to the magnetic field, and there is going to be even more strangeness coming along once we get to electromagnetism, light, and then some of the effects of when it comes to relativity. But we're saving that all for later.